So here in part 5 we pick up where we left off. We'd gone back in time a little bit to look at the work on the H17 drives while we were waiting for the RAM chips to arrive, and we'll just manage to rebuild the board, swapping the damaged capacitors out. So we're going to pick up the story where we put that board back into the H17 and see how we get, and hopefully we'll catch up with part 3 RAM repair finally and get back on time track. Okay, I've used the meter just to make sure there was on diode test at each of the transistors, and what I assume is another power transistor maybe, perhaps the stepper drive control, who knows. Just make sure on diode test that there's no dead shorts across them, make sure that the caps have got either quite high impedance or some resistance, there's no dead shorts across a couple of the chips. So I think it might be just safe enough with it out of the frame just to power the board up and just make sure we get sort of 5 volts on the TTL logic, and we don't take out the 12 volt feed as well. So I'm going to find a useful negative spot to stick my thing, so we should be across the 2 caps. We should be able to see the voltage is stabilised, and hopefully the dim bulb won't glow too badly. Okay, we've just got a very dim glow, so across that one now I should see a stable 4.97 volts, and across this one I should see 11.88. So at least nothing's dragging down the 4.9 something across several of the TTL chips. Yep, 4.96 volts, so it's looking good. Some of them might just, I'm not sure, some of them have different pinouts, but just the ones I know. Yep, so we got reasonable. Looks like that board is now not pulling anything apart and getting the voltages it needs. So it's quite a good start. Need to clean up and service the drive mechanism next, and then we can do some of the drive tests to make sure things are working. It doesn't actually look that bad, the drive mechanism, so maybe I'll just go and get we could just do some basic test and just see if it powers up and the H8 can detect the drive mechanism at least, and some of the initial tests in the system. I clean that bar off though, because that's just got some corrosion on it. It's going to cause difficulty for the worm drive. Okay, let's get that bar cleaned up and a little bit of machine oil on relevant parts that need it, and we'll come back. Powered up with the board still in there. We've still got hopefully 12 volts and 5 volts. Yep. So obviously no motion. I haven't got it plugged into the H8 or the controller. Need now to test out the H8 itself, make sure that's alright before we plug this in. So I'll reposition the camera and have a quick look at the H8. So I'm going to power up the H8, make sure it still works today, which it does. I suppose we could just do the memory test. So if I go to alter the register for the program counter, alter it for 03003, which is the memory test area, and then finish altering, I do a mem of 05000, then I do a go. And a second go, if I monitor the HL register, that's the address it's going to start at. So if we hit go, it should test and find the error at 106265, which we did. So controller board is running. I won't retest the RAM on the controller board, but we do know that we've got a fault at that memory address. If I go to reg HL 106, you'll find that it's flickering because it's not got a value in there. Whereas the address before, yes, it's not sure about the bit at that address. So if I set it to 377 and go back, it's not quite sure. There's obviously a bit fault there. It's slightly different to what it was doing yesterday. That bit is definitely intermittent on those RAMs. But hopefully that won't be enough to stop us being able to at least do some initial testing on the drive. I wonder whether I need to take it off the dim bulb a minute, although it seems to be generating the 5 volts fine. and if something does happen, at least it'll have a little bit of a protection. Okay, well I've just checked that the serial port will output a character to the thing, which it will. We're not going to need it yet, but I just want to make sure that the serial connection was up. I've got that in. We're going to try and do now, connected the cable. So what we need to do is press the reset the machine. You're going to press the mem 0, which is following the notes in the book. So 020 177 out. I spec, does it? Yep. And indeed the drive motor starts. Yep, and I can see the drive spindle rotating. It's a good start. So if I do mem 00177 out, I assume that's going to shut off the motor drive. Good start. Okay, so do a mem 002 177, press the out key. Okay, front indicator light came on. When I reset, the solenoid goes on and off. So that's a good one. Let's repeat that with the drive door closed. Mem 002 177 out. Nice, and reset. Yeah, okie dokie. So we're going to do a read-write test. Turn off the floppy disk, remove the two screws that hold the top cover of the floppy disk unit, remove the top cover. So to make sure the programming plug is 8 jumper, this is one of the funny ones, I think. The programming plug is only 6 strips. 1, 2, 3, 4, 5. It does indeed, yes. I think that's because this is a Wanko rather than a Siemens drive, but I'm not sure. Refer to part A. If the programming plug is only 6 jumper screws, refer to part B. Good idea to circle, put a check mark beside the appropriate part. Yeah, brilliant. So now we don't know. Examine the DS1. If it's not been cut, proceed to the next step. If it's been cut, really carefully track solder wire. I believe this is set correctly because it's got DS3 still connected, and I think the drives go in reverse order. So DS3 is the first drive. I'm sure I've read that somewhere. So basically, it's cut strips DS1 and DS2 are the plug if you're doing it, yeah. So that's SY0 then. What I've got, these are soft sector discs, but I just want to run the drive up with a sacrificial disc in. I'll probably use one of these as a, if I can. Ooh, see, it won't go in, that's exactly why. Oh, actually, it probably is. It just doesn't go in because you close the door, you expect it to go further in. It's interesting. So, I doubt it's going to do what it's supposed to do, but let's have a little look. Press the reg key. PC, so we're going to set by altering. It doesn't explain what you're doing at each step. That's the only criticism of these. It's really good. So what I'm doing is I'm setting address 003000, which is the first address in the ROM, and I think that is the boot sector attempt. Alter to go back out of it, and go. And the light's glowing a bit more dimly. Drive units to be selected, front panel indicator, H8 will be on display 037127. I think it's failing because it hasn't got a disc in it. Yeah, there we go. Alright. But at least we know it spins and turns, and I can visually inspect the disc to see whether there's any damage. There doesn't seem to be at all. So that's good. So the acid test is, do we actually try this? Do we try the only disc we got in the drive and see if it boots? It's an interesting moral dilemma, I suppose, but because it is, although it's not a blank disk, it's formatted soft sector. I'm sort of tempted to just try booting the thing purely because I've no reason to suspect the drive is not functional and operational. But obviously there are some adjustments that need to be made. I don't think it's going to physically damage the disc, hopefully. So we'll give it a go, shall we? This should boot from the disk. Whoa! You're not going to believe this. I've now got on the display, look at that, action boot. Ah! Good grief, I think it's actually working. So I'm not sure what the answer is for action boot, to be honest. I think it's 1, isn't it? Don't know. We're going to have to go and read some instructions, aren't we? But it's definitely actually running, and the disk is operational. Whether there's actually anything on it to boot from, I don't know. So now we need to read the HDOS1 manual. Didn't expect to get that far. And see what we can do to actually start the disk. Okay, let's have another quick go. I suspect we'll only get 1 or 2 attempts at this because the oxide will wear off the disk, and I don't want to damage the disk. I will go off and try and find some hard sectored disks, because it could also damage the head on the drive perhaps. So one more try and then we'll call it a day and try and get a better quality image disk and some hard sector disks to carry on playing with it. Okay, so reg PC alter 030, oops, alter 030, hello, alter, and then go. This should start to try and boot. Right, action boot, carriage return. Now that locks up. I've been having this problem with the, I think it's the IRQ, is interrupting the machine and then locking it. I was getting that with just the serial card. So we'll eliminate that and then we'll come back to the problem maybe, because that isn't it. So let's shut the drive down. So the next fault we got to sort out is why when I send a character to the serial card, does the machine lock up? That's obviously an interrupt request problem. Something's happening in the machine that's causing the interrupt. It's being triggered to say there's a character, but then it's not dealing with it correctly. And in order to find that interrupt, we're going to have to reconfigure. We can do it without the H17 hooked up. Slowly getting there. Hopefully we'll have the replacement RAM through as well, because it could be due to the faulty RAM error. Although it's in a middle bank, it could be ending up being used for some reason and we don't know about it. But I don't think it's a problem on the controller board yet. It's definitely the, you see it even without the controller board. I did set up the analyzer again and added some scanning for when the IRQ was triggered, and looking through some of these traces which capture the instructions. Once I actually put them into octal, it turns out I was capturing the data bus inverted. I'd forgotten to turn it negative. So I did correct for that, and that's why it's now shown in octal. But basically the trace shows that the system is correctly doing as it should do and running through the RAM vector, and it's empty, so it's just cycling round in the middle of nowhere, looping in within the ROM, basically waiting for a key press that never comes. So in real terms, what's failing to happen is the system is not setting up an IRQ vector, so it just doesn't know how to deal with that. I'm sure you've worked out from the varied lighting that sometimes I shoot in the night when I'm got something I want to fix, and the IRQ problem was definitely when I wanted to really work out a way around it, and I came up with a fairly brutal solution. I got a little bit of footage because that did allow me to get as far as or past the boot menu by pressing return, and actually I had read by then that if you typed help at the boot prompt, it would give you a list of things to do. Indeed, we managed to get it to boot, and this menu appears. And of course the obvious logic was to try a cylinder check, because how much harm could that really do? It's just going to be reading the disk, and we knew that the drive was running, so off it goes. think the system has actually crashed at this point, so I can't type anything in. It could be the bad memory has started to take an effect. So there we go, we fixed the memory, we might actually get somewhere. So that's HDOS version 1.5 boot in, and all I had to do was pull the interrupt generation chip out of the serial card. Looks like you don't have one in, there's no driver, no vector, nothing. There we go. We're going to have a look now at the current state of the machine after I worked that out and how I worked around it, which actually is a bit of a hardware hack until I just can't see how it's working exactly as designed, so I can't see how it worked originally. You must have had to do some sort of patch of the vectors. I did try booting the HDOS ROM and then exiting it and going back in, but that wipes the vector again. So this solution, which we'll see at the end of the short catch up with the cards, is pretty much how I fixed it. The 4K card is now actually been upgraded, as you can see. We've I've still got some new buffer chips in this one because it had did have one or two faulty, but I haven't swapped in the originals yet. But I have put the new sockets on to populate the missing part of the board, and mostly the newer RAM chips. There are a couple of the originals, quite a few faulty ones on this 4K RAM chip board. Unfortunately, as I suspected, I think there's actually only about 4 original chips on there. The rest are all new ones. So we're doing all right though. We've got an 8K card, and the jumper has been set back to put it at the 24K position, so that it allows us to have it just above the 16K RAM, which gives us a full 24K of memory. So the 16K RAM card, you can see where I've swapped out the one row of chips completely. I didn't bother diagnosing which individual chip had a faulty bit in it. It was seemed to be quite inconsistent, and that's a known set of 8. And now I will eventually test the others and use them as spares then for if any of the other 3 rows go on. I have restored the original buffer chips, so they've still got the dirty legs. They still need proper cleaning. We'll do another pass through each of the cards for a clean. I think the floppy controller was probably built at a different time, maybe even by a different person. The stickers on the chips are not present on the other boards. They are original, and I didn't have to do anything with the board. It just works when it's plugged in, which is a really good start. Okay, with the 2 RAM boards removed, you can see the board. Let's put a bit more light on it. So this is the H17. I've still got the connectors for the Hewlett-Packard analyzer hooked up in case you need to do any more diagnostics on the bus. And this is the little switch I've rigged that just connects, if you can see down there, onto the interrupt 3. It replaces the jumper, so you can turn either the connection on or off, so the interrupts actually come through from the USART or not. I've also got the send, receive and ground hooked up to the TTL connection, and I put a jumper in on the 9600 board and the 600 board. I put a pin in each of those. You could put them all across if you want, so you can change the clocking rate. That's because I'm running at 9.6K at the moment, but these opto isolators, I've been told, prevent the board from running at 9.6, a maximum about 4800, so it'll go back to the 600 for operation with the H9 for authenticity anyway. Although the USARTs are both replaced and working, you can interchange them, and the transmission will be fine. And you can also use the port interchange to swap the which USART is used for the dump and load commands from the monitor, so you can use the serial port to dump and save. I haven't actually got the analog side of the circuitry running, although I haven't made up a cable. There's still no actual signal on the scope showing. So that's about where we are with that serial card. So to really take a look at explaining that problem, because it seems that if when you press return on the initial presentation of the boot message, the HDOS boot ROM, and we'll have to disassemble that, doesn't seem to need any interrupt to happen. It reads the characters without interrupts. It's obviously just taking them, but for some reason that's not clear in the USART buffer. Now whether there's another error I can't find or I don't know, but basically that allows you to get past there. You can type characters in to do the disk check,
or to type boot or press return to carry on the boot, and then HDOS will get all the way up to having the date, and at that point it is in its proper setup where the interrupts are supposed to be gathering the characters, so you need the interrupts enabled for that. So let's take a little look at the circuit diagram and explain how we get characters in. Now I did posit it might be the RAM, no, because the fixed RAM still had the problem there. It's been suggested because the serial card can't work above 4800 baud. It's not that, as we'll see, because we bypass the components that cause the reduction in performance and speed, the opto-isolators, by directly injecting TTL. So the just to be clear, at the moment I have this IC122 removed, which means that my data in line is coming in here from the TTL connection, coming down, 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 and if we go down it'll go all the way into the received data in this USART. And just to make it clear, therefore, the limitation of this card is that apparently this opto-isolator's response limits the baud rate to effectively 4800, makes 9.6 unreliable. Because that's not in the circuit and I'm injecting the TTL data directly here, I shouldn't have that problem. It should be nice clean signal, which it is. I mean, there is no problem with the data coming in. The 8 data bits get in and they create this connection quite usefully, and the characters are received perfectly well. And the same when it sends out data, I've got the same thing here. It goes up the TX line, and obviously I don't have this gate here. I've just pulled this straight out into the other serial line, so I'm plugged in here. So this gate is gone as well. So data out and data in a clear serial. Once it's got all 8 bits needed to form a character, it will assert the RX ready on pin 14, which means that it's got a received character. So that goes along the cable and into IC129D, one of the gates, which is a NAND gate. The other side of the NAND gate is permanently held high there, so it basically just gates through and acts as an inverter for that signal. So when it's high it'll be low, and when it's low it'll be high. Irrelevant. The manual asks you to, and this is the way, because the USART is quite flexible, it can generate signals when it's got a received character, when it's transmitted a character, when the buffer's empty ready to receive another character for transmission, and when the SYN flag is set. So basically the jumpers on the board allow you to select different options. In the case of the manual, obviously it says you want a link from the receive connection. So that basically means whenever a receive character is ready, it'll come out along this wire, which then goes down here and goes to this other jumper on the board, which is the interrupt level select. And the manual asks you to make that down to interrupt 3. So this basically means whenever a character's level is received, it will assert I3 onto the Benton Harbor bus on pin 3, and the CPU card will then go to the ROM, say, oh, it's a level 3 interrupt, that's a user level 1, look in the memory area allocated for a vector, a jump address, and try and jump off and do whatever that does. Now the problem I had is that for some reason HDOS at the boot prompt doesn't like receiving an interrupt. It's happy to read a character, but the problem is if the interrupt happens when you press the key from the serial terminal, it jumps away and crashes the machine, so HDOS never gets to see that character. So my solution was just to tear out IC129. So when I pressed the character, basically this chip didn't exist, so nothing went on the wire, nothing went on the interrupt, and nothing happened. And for some reason it saw the USART character. I'm wondering whether it's got some code in there to try and do something just to poll it. Whatever happens, it gets the character and off it goes and gives you the boot menu, and you can then carry on to actually get the machine to boot quite happily. The difficulty is then when it gets into actual HDOS loaded, you can't type the date prompt window, because by then it is expecting an interrupt handler to say there's a new character has arrived in the buffer. I need to dig deeper into the actual disassembly of HDOS to find out why. So my second solution then was to make this link removable effectively with the switch, which allows me to quite simply not have an interrupt for the boot prompt, then flick the switch over, and then when it gets down to the date, it starts generating interrupts. That's effectively my workaround at the moment for this card. Just out of interest, while we're here, the port interchange switch, you can see that's quite clever. It just which address is selected to decode, and basically all it does is acts as a changeover as to which USART is selected, depending on, because here's the chip select. So in one position it will be this USART selected, and in the other position it'll be the other one. So just basically this decodes the IO address as 340, I think it is. So basically it just allows you to flick which USART gets that IO address, and obviously the other one gets the other IO address that's been decoded, because you could have wired them directly down to these wires, but they'd be fixed then. So putting it through the interchange switch allows you to flick over which gets the dump. So that's how the card works. As I say, it's working as expected. It's just HDOS doesn't seem to know what to do with that initial connection. With hopefully everyone now understanding the problem with the IRQ and how the temporary solution is working, I was able to go back then, because I initially didn't have any hard sectored floppies. I started looking into a semi-virtual disk, which is the emulator for a hard sectored disk drive, and we'll probably cover that in a future episode where we actually look at using HDOS on this. So there's a little bit out of order. The device does contain the front panel that has the serial connector that's used by the SVD. With that solution we can get past the boot prompt to the date, type it in, and finally get into HDOS. I think we'll leave it there at part 5A as it's going to be. I think we'll have a part 5B because I've already pretty much completed part 6. So, but you're going to, in the second half of this part, we will actually do a bit more of a dive into the semi-virtual disk and some detail on using HDOS utilities to format disks. But I think we'll play out with actually getting the H8 to boot up from a system disk that we've made and go into HDOS and just have a little look around. So hopefully we've got a way of capturing now the actual screen, so I can stitch that in afterwards. What I'm going to do is look at starting that Minicom, which we use in the -S option, which allows us to go down to the serial port. I don't have the second USB connector set up yet, so the serial interface will be dev TTY USB 0, and I'll set a 9600 baud parity and no parity, F for hardware flow control off, and then we can just go into the Minicom system and we're ready to go. Now hopefully when we boot the H8 we should see the screen appear. So I'm going to use the original boot disk because we're going to go through what you do to make a new system disk. So there we go, in the drive. What I'm going to do is reg pc alter 030 and alter again, and then go, and the machine should boot, which we've got the action boot prompt up on the console. I can press return. The screen got blank because interrupts. I've got my little switch to disable the interrupt to bring it back, and now I can put it back again to interrupts because HDOS will have loaded its vector tables and we'll be able to handle the settings. I already booted this earlier, which is why the date is set to 30th of June 1989. So I press return. We'll get another disk ready to have a play with, which I'm going to assume they were blank. And put this out of the way a little bit so we can see what we're doing. So now we have a booted version of HDOS. So hopefully you'll join me in the second half of this part, so we can have a dive into that. See you soon.